Hello, physics students. So I found this very old device in our storeroom piled under a bunch of junk. I pulled it out and I cleaned it up, and I found that it does something very interesting. What it's going to do is it's going to put some energy on this spot right here. And then we're going to see what it does. I'm going to show you what it does. But first, I'm going to step out of the way because it's a little dangerous. So watch this spot really carefully. Pretty amazing, isn't it? And no, we're not watching some Harry Potter movie. Once again, I'm demonstrating something very interesting and very unusual, something almost magical that appears on the subatomic level, which is the topic of today's video, something called pair production and pair annihilation. So let's go to the board and I'll show you what that is. If you change the scale of the little magic that I just did, then eventually it will actually happen. What you have to do is you can't use visible light in the electromagnetic spectrum. The photons of visible light are too weak, too little energy. If you increase the frequency and get up into the X-ray or the gamma ray, and then you bombard that and hit a target, what can happen is you can create matter, objects out of that energy. But of course, they won't be bananas, they'll be particles and antiparticles. So that's what we have diagrammed here. The process called, first of all, pair production, then we're going to talk about annihilation. But in pair production, before you have a high energy photon, maybe I'll even write X-ray or gamma ray. It's a target, and then what happens in this case, I had an electron and an anti-electron, which we call a positron. And so the photon, the energy disappears, and in its place we've got two particles appearing. Then they're in a magnetic field. Since they're opposite charges, they spiral away. But you could also make other particles, not just the electron. Now this is different than what I was talking about in the quantum physics video, where we had a wave function, and so electrons were these imaginary things, and then when a human did an experiment, they would appear as particles in a random location. So that's different because the electron still existed as the wave function. In this case, there is no electron, neither a particle nor a wave function, and you create them as a result of the energy disappearing and then matter appearing. Now, another thing that I want to say is that of course, these are created in small quantities. You make a single electron and a positron, or maybe a proton and an antiproton. But the problem with this is that as soon as this positron, anti-electron, spirals and touches any other electron, it'll disappear in what we call pair annihilation. I'll talk about that in a second. That's the nature of antimatter, very interesting. But in theory, I suppose it's possible to keep repeating this and somehow isolating the anti-electron, the antiproton, and maybe I make an anti-hydrogen atom, or maybe I make an anti-carbon atom, or maybe I make a whole sample of something that we could see with our eyes. Now, if we did that, somehow we would have to trap it away from everything, even air. If air touched it, it would annihilate, and there would be a tremendous amount of energy. And I'll just mention this as briefly as I can. There's actually a book by Dan Brown called Angels and Demons. It's one of those page turners that you read, and they made a movie out of it even with Tom Hanks. So it's a very interesting, fast-paced book, and the key part of it is that a villain steals antimatter from a lab, and there's like a 1/4 gram of antimatter suspended in a magnetic field, and when the batteries run out in that little chamber, the antimatter will fall and touch matter and be like a nuclear bomb blowing up. So that's, the premise of the book. And if you want to read the book, very exciting. I didn't give away too much. Basically, all that I said is revealed in the first 20 pages, and then it's one of those thrilling books. But anyway, just that's a side topic. You can create this particle at a time, but if you wanted to make more of it, you'd have to keep it isolated. That was just the point I was trying to make. Let me create a pause to allow you to copy this down. All right, now, the analysis. if we wanted to do this in experiment, we can't just use any old photon. It's got to be the exact right photon for this to happen. So how do we figure out what photon we need in order to produce an electron and a positron? Here's the analysis. Now, both momentum and energy have to be conserved. In this case, momentum is definitely conserved because a photon has momentum, and then these two have momentums. So that's what this is saying. The momentum of the photon is initial, then it goes away, and we have final. These two have momentum. Whatever kilogram meter per second we have here, we have after also. That really doesn't help us too much in our analysis. If we want to go in more detail, we could use that expression, but we're just going to try and keep this as simple as possible. And so then we're going to analyze this from an energy conservation perspective, because the photon is energy, as I mentioned already, and we learned in the first video in this topic on photons. So that energy of a photon is hf, Planck's constant, front cover of the reference table, this being the frequency of the photon. Now, when matter is produced, as we learned in the nuclear topic, mass and energy, same thing. When you gain energy, you gain mass. When you gain mass, you gain energy. So we gain mass, so that has a certain energy certain energy that it corresponds to by mc squared. This is the mc squared of the electron. This is the mc squared of the positron, right? The symbol of the anti-electron, we put a bar over it. And then also these two have kinetic energy. But to keep it as simple as possible, we're going to assume the kinetic energy is negligible. And you could show that in a calculation. But basically, by crossing this off, I'm creating a little bit of a percent error in calculating this in this analysis. Now remember, a particle and antiparticle have the same mass. So this is the same mc squared as this. So we can combine them into 2mc squared. And this is the basic equation. So this is if, for example, we knew we wanted to create an electron and a positron, we plug in the electron's mass here, and we'd solve for the frequency needed. And if you did that, I'm not going to do it because it's just number crunching. But if you do that with the speed of light here and Planck's constant, you would get 1.24 times 10 to the 20th hertz. Remember, light is 10 to the 14th. Way too little energy to create an electron-positron with visible light. But what is 10 to the 20th? Well, I'll come up here close so you could see the electromagnetic spectrum. And you see 10 to the 20th frequency is over here. And if you look at what that is, you could either call it an X-ray or a gamma ray, as I already said. So that's, you need a very high energy photon to produce pairs of particle-antiparticle. Or you could say, I have this frequency, what kind of particle can I create? So it's basically an equation where you're going back and forth between frequency and mass with some algebra. So let me create a pause to give you a chance to copy this down. All right, so we made an anti-electron or positron, and then, as I said, it goes off and spirals, and as soon as it touches even an electron in an air molecule, right? So this would have to be done in a vacuum if you wanted the positron to last for some amount of time. But as soon as it touches another electron, they're opposite charge. The electron's negative. The anti-electron or the positron's positive. They attract and stick together, and then as soon as they touch, they vanish. And they disappear, and only energy. And it's almost the reverse of this, but not quite. It's not exactly a reverse process. So let's take a look at that now. All right, so here's a diagram of what happened. By the way, I can't do the magic trick that I showed you with the bananas because this is a true story. I got hungry and I ate the bananas, so I apologize. So one less interesting demonstration to show you. I guess I did annihilate them in a sense, but they're annihilated in here. So anyway, but you have the two particle-antiparticle touch, and then after, remember before in the diagram I just erased, we had one photon create the two particles, but now the two particles don't create one photon. They must create two photons. Two photons must be created. Why? So the reason why is, let me create a pause to allow you to copy this down. All right, the reason why is because, again, momentum is conserved. So the momentum before, if these two come together, and even if they're moving at each other, or if they just touch with very little velocity, the momentum, if they're coming at each other, zero, positive momentum, negative momentum, or if they're not hardly moving, then it's still zero also. So P initial is zero in this case. And then P final must be zero. And how could you have zero momentum with one photon, one object moving? You can't. You've got to have, if there is something moving, to have zero momentum, you've got to have something moving in the opposite direction. That's why we need two equal photons here. And remember that the momentum of a photon is h over lambda. Maybe I'll just write like this, because you might not remember that. Let's say P photon 1 plus P photon 2. And so this one, if it's positive, then this one, well, maybe the one going left is negative and this one's positive, and they add to zero. So you need two photons. The energy expression also is true, E initial equals E final. But this time, what we had before, by the way, that arrow there in your notes, I hope it was there in the notes. That's what I want you to focus in on, the emphasis, because that's the key thinking of pair production, pair analysis that allows you to solve the problems. So the key thinking here is, what do we have before? Well, we've got a particle and an antiparticle. And then after, as you see, we've got two photons. And so notice here how we have a 1 here and then a 2. I'm going to erase this now because I need the space. But here what we have is 2mc squared on this side, because these are the same masses, and 2hf on this side. So the formula is different. 1 versus 2. Now we've got 2 versus 2. All right, 2 and 2. I guess I was going to write another line, but I don't need to. We still, because you could see the 2's go away. And we, again, have an expression, a slightly different expression between frequency and mass. So if we say, well, what kinds of photons are created when the anti-electron or positron spirals away and touches another electron? Well, we can plug in the electron mass here, speed of light, Planck's constant, solve, and basically the frequency is less this time, half as much. It's still a gamma ray, still an X-ray though. So there's the analysis for pair annihilation. Let me create a pause to allow you to copy these notes down. All right, so that was pair production, pair annihilation. Pure energy creating matter. Another magical thing that happens on the subatomic level, particles and antiparticles. So pure energy creating pure matter, and then the reverse of that, pure matter disappears and creates pure energy. So very interesting phenomenon. I hope you enjoyed the magic I had at the beginning of the video. I hope you enjoyed the physics. I'll see you in the next physics video. Hello, I'm back again. I just realized after I stopped the camera that I said, see you in the next physics video. But there won't be another physics video, because at this point, you've completed our entire physics course. So, of course, we'll meet in class, we'll be doing some review before the end of the year, but no more physics videos. So I guess I should close out this physics video saying, thank you for joining me. I hope you enjoyed the videos, the physics, all the magic that we did. I hope that you have developed an interest for physics. Maybe you're interested in studying it later in college. Or maybe you want to buy a book on physics. Yes, they sell books that are bestsellers, like Stephen Hawking has a lot of books out. People who don't know any physics read them because physics can be so fascinating, as we saw in this topic, and they get into all that philosophical stuff and maybe spare you with the math and just give you the interesting ideas. So maybe you'll read a book on physics. That's my hope. So I guess I should close out saying thank you for watching. Congratulations for completing a great year. And I guess I should say take care or goodbye or something. So again, bye-bye.